Hello, welcome to a new lesson in classical mechanics. Today we are going to study an important concept known as point transformations. And we know that we study some mechanical systems that we know that are described by some particular Lagrangians, right? If we know what is the Lagrangian of a mechanical system, we can establish what are the equations of motion through the Lagrange equations. Okay, so we know that associated to this mechanical system, we have a set of generalized coordinates q1, q2, all the way up to qn. Okay, so a point transformation is going to be a transformation of the form qi equals to qi, which is going to be a function of s1, s2, all the way up to sn, and the time, where of course n is the number of degrees of freedom of the mechanical system. So if we have a transformation of this form, we are going to name this as point transformation. Okay, so we are going to be interested in showing that these kind of transformations leave the Lagrangian, or actually the Lagrange equation, invariant. Okay, so that means that if we have a Lagrangian, that we know that usually it depends on the qi dot, and the time, then we are going to transform this with a point transformation to a Lagrangian that is going to be a function of sj dot, and the time, right? Because if qi is a function of s, qi dot is also going to be a function of s and sj dot, and well, the time remains the same. So that means that our new Lagrangian is going to be a function of sj dot, and the time. Okay, so you might be wondering what happens with the dependence of qi dot. I mean that if qi depends on the s and the time, qi dot is going to depend on the s, the sj dot, and the time. Okay, we can see this with an easy example. Let's say we have this coordinate transformation q equals to x squared. And then if we want to calculate q dot, we see that this will be 2x dot. Of course, here, this x is a function of time. Okay, so we see that q dot is a function of x and x dot. Okay, perfect. So that is going to be important. Just remember that qi dot is a function of sj dot, and the time. Okay, so what we are going to do now is to establish the Lagrange equation form for this Lagrangian that we have here, and we are going to see that it is also going to be equal to 0, even though we have made this change of coordinates. Okay, so we are going to start by calculating the derivative of the Lagrangian with respect to sj, and we know that the Lagrangian is a function of qi dot, and the time. Okay, so if we want to calculate this derivative over here, we need to use the chain rule, looking that the variables that depend on sj are qi dot. Okay, so we are going to have here the derivative of the Lagrangian with respect to qi, and then the derivative of qi with respect to sj, and then we will have the derivative of the Lagrangian with respect to qi dot times the derivative of qi dot with respect to sj. Perfect, just by using the chain rule. So with this, we have the first element of the Lagrange equation. Then we will be interested in calculating the derivative of the Lagrangian with respect to sj dot. So what will this be? Well, the first element will be the derivative of the Lagrangian with respect to qi times the derivative of qi with respect to sj dot. But we can see easily that this element is going to be equal to 0 because we know that qi does not depend on sj dot. So automatically this is 0. Perfect. So then we will have plus the derivative of the Lagrangian with respect to qi dot times the derivative of qi dot with respect to sj dot. In this case, this is no longer 0, right? Because we said that qi dot depends on sj dot. So we can say that the derivative of the Lagrangian with respect to sj dot is equal to the derivative of the Lagrangian with respect to qi dot times the derivative of qi dot with respect to sj dot. So this will be another element of the Lagrange equation, right? We just need to take the derivative with respect to time now of that element over there. So that will be this thing over here. And looking that we have a product of two functions, of course, these two functions depend on the time. So that means that we need to use the product rule to calculate this last element. So what will this be? It is the derivative with respect to time of the derivative of the Lagrangian with respect to qi dot times the derivative of qi dot with respect to sj dot. And then plus, it will be the derivative of the Lagrangian with respect to qi dot times the derivative with respect to time of the derivative of qi dot with respect to sj dot. Okay, perfect. So with this, we have the last element that we need to construct the Lagrange equation structure. So let me write that equation down here. Okay, so here it is. You can see that this has the structure of the Lagrange equation, looking that this element corresponds to this derivative, and then we subtract the derivative of the Lagrangian with respect to sj, which is all this thing that we have here. Okay, so we need to work a little bit with this expression to see what are we going to get. First, we are going to do something interesting. You should know that, well, we have a very common used relation in Lagrangian mechanics, that is that the derivative of qi dot with respect to sj dot is equal to the derivative of qi with respect to sj. As you can see, we are only eliminating these dots, right, to get this expression over here. So it is not very hard to show. Let me do it quickly. First of all, we need to establish that qi is a function of sj and the time. So what happens if we take the derivative with respect to time of qi? Well, we'll see that is qi dot equals to the derivative of qi with respect to sj, and then we need to take the derivative of sj with respect to time due to the chain rule. So that will be sj dot. And then this will be the derivative of qi with respect to time, right? Okay, perfect. So from here, it is easy to notice that if we take the derivative with respect to sj dot of qi dot, well, we are going to get this element that we have here. So with this, we conclude that the derivative of qi dot with respect to sj dot is equal to the derivative of qi with respect to sj. Okay, so again, this is a very well-known result in classical mechanics that is often used. So, okay, so how are we going to use this result? Well, you will see that we can apply that formula to this element that we have here, maybe. But first, you should notice that we have this element here at the front that corresponds to the Lagrange equation first element, right? We know, again, that the Lagrange equation for the q's tells us that the derivative with respect to time of the derivative of the Lagrangian with respect to qi dot minus the derivative of the Lagrangian with respect to qi is equal to 0. So this equation is telling us that this element can be transformed into this element that we have here, right? It is equal to this element. So we can rewrite the equation that we have as follows. It will be the derivative of the Lagrangian with respect to qi times the derivative of qi with respect to sj by using this formula, and then plus the derivative of the Lagrangian with respect to qi dot, and then times the derivative with respect to time of the derivative of qi dot with respect to sj dot, like this, and then minus the derivative of the Lagrangian with respect to qi, the derivative of qi with respect to sj, and then minus the derivative of the Lagrangian with respect to qi dot, the derivative of qi dot with respect to sj. So from here we can see easily that this element is going to cancel this element over here. Okay, so what are we going to left with? Well, we see here that we have this element that is the derivative of qi dot, and this qi dot, of course, it can be seen as the derivative with respect to time of qi, right? But we are going to switch the order of the derivatives to take the operator, the derivative with respect to time outside. So we are going to be left with the next. It will be the derivative of the Lagrangian with respect to qi dot, the derivative with respect to time of the derivative of qi dot with respect to sj dot for this element, and then minus the derivative of the Lagrangian with respect to qi dot times the derivative with respect to time of the derivative of qi with respect to sj. Okay, perfect. So again, using this relation that we showed, we see that this quantity is equal to this quantity over here, and then we have a subtraction of same elements. So that means that this cancels with this, and we see that we get 0. Okay, so this is showing that the derivative with respect to time of the derivative of the Lagrangian with respect to sj dot minus the derivative of the Lagrangian with respect to sj is equal to 0. And this shows that making a point transformation to the Lagrangian makes the Lagrange equation to be invariant. Okay, so I think this will be the important result of the lesson. Okay, and just by a curious fact, I'm taking this information out of the book of Goldstein's in classical mechanics. And this book presents a very interesting problem that tells you to find or to show that some particular Lagrangian that I'm about to write, this Lagrangian over here, well, it can be seen as another Lagrangian that is transformed by a point transformation. Okay, so actually the problem gives you this Lagrangian. It tells us to calculate the equations of motion, and with that equation and some other conditions, it takes you to find that that Lagrangian is actually the Lagrangian of the harmonic oscillator, which is very well known as 1 divided by 2m times x dot squared plus y dot squared minus k divided by 2 x squared plus y squared. Okay, so the book tells you to show that this Lagrangian is equivalent to this other Lagrangian just by making a point transformation. Okay, so I found that a trivial transformation that we can make to get from this Lagrangian to the other one is to establish, for example, that x is equal to some constant a times q1 plus some constant b times q2, and then establish that y is equal to 0. Okay, so with this, we can say that x is a function of q1 and q2 that is equal to this expression over here. And then y is also going to be a function of q1 and q2, but it is the function 0, right? So it doesn't matter too much. Okay, so it should not be very hard to do this. I mean that if we calculate x dot, that will be aq1 dot plus bq2 dot from this. And then if we substitute this value into our Lagrangian of the harmonic oscillator, we'll see that we are going to get a Lagrangian of this structure. Okay, so let's do it. I mean that the Lagrangian, which is going to be called L prime, is going to be 1 divided by 2m times x dot squared, but that is aq1 dot plus bq2 dot squared, and then plus y dot squared, but of course y dot is equal to 0. So it will be 0 squared, and then minus k divided by 2 times x squared, which is aq1 plus bq2 squared. Okay, so from here we are going to get that 1 divided by 2m times a squared q1 dot squared plus 2 times a v q1 dot q2 dot plus b squared q2 dot squared, and then minus k divided by 2, it will be a squared q1 squared plus 2av q1 q2 plus b squared q2 squared. Okay, so I think that with this is enough to see that this new Lagrangian already has the structure that we are given with this. Recall that this is L prime. Okay, so look that we have a constant times x dot squared. So we have this constant a squared q1 dot squared, and then plus 2 times b, which is another constant, x dot y dot. In this case, let's say, of course, that the role of x is being played by q1, sorry, x, and then the role of y is played by q2, okay? But that doesn't matter too much. I mean that this Lagrangian is going to be a function of q1, q2, like this, okay? Perfect, and again, we see that we have plus a constant y dot squared. So we have that, a constant times q dot squared. And then we have something similar in this expression. We have a x squared plus a constant xy plus a constant y squared. And that is what we have here. We have a constant times q1 squared plus a constant times q1, q2, and then a constant plus q2 squared. So with this transformation, this one over here, we have shown that this new Lagrangian is equivalent to the Lagrangian of the harmonic oscillator just by making a point transformation like this that we have over here. Okay, perfect. So I think that with that example, I'm going to finish the lesson right now. And thank you so much for watching.